This is the Irish Sea. Under its waves, a pipeline extends 1.5 miles from the shore, and through it is pumped radioactive waste. It comes from this plant at Windscale, Cumbria, a plant which reprocesses fuel from Britain's and other countries' nuclear power stations. The British government says that pumping this radioactive waste into the Irish Sea from Windscale is safe, but some new research by American scientists is challenging this view.
It means that populations in this area are under, I believe, extreme hazard from, you could say, possible remobilization of these accumulated releases, and I would say from the certain eventual remobilization of these accumulated releases.
Assessing the risks of nuclear power means research at the frontiers of scientific knowledge. The whole area is baffling to the lay public and surrounded by controversy among the experts. Yet the issues involved are of great public importance. Recognizing this, the Secretary of State for Energy, Tony Benn, called for a wide-ranging public debate on the issues raised by Britain's atomic power programme. So that he and the British public could decide on the basis of full information, last February, Benn posed a series of questions which he said should be answered by those planning our nuclear future.
Is the work upon which you are engaged being done, or has it been done, or has it been started and stopped in other parts of the world, and what experience is available from abroad that might help us to assess your own proposal?
World in Action went abroad to America to report on the latest research findings from scientists concerned with the problems of radioactive waste. Tonight, as a contribution to that public debate, we present some American views on the risks posed by nuclear waste in the Irish Sea. This pipe carries waste from Britain's nuclear reprocessing plant to the sea. To understand the worries of some scientists, it's necessary to understand the nature of this waste. It's contaminated water, both from the ponds used to cool the spent fuel rods and from cleaning in the plant. It consists of some of the same radioactive materials at much lower concentrations as the deadly high-level waste. High-level waste from the fuel rods has to be kept apart from the environment for hundreds of thousands of years. But low-level waste is released into the environment within government limits. The radioactive elements in the waste that concern scientists most are called the transuranic actinides. They emit alpha particles, the most dangerous of all radiation at close quarters. It's the unexpected behavior of these actinides that's causing the present controversy. This field of science is less than 40 years old and can still give scientists unpleasant surprises. One such surprise came recently here at Maxey Flats, a low-level waste dump in America. Until recently, scientists believed that plutonium, the major actinide, would stay put in the ground. At Maxey Flats, they found they were badly wrong. In November of last year, Dr. Mayer of the US Environmental Protection Agency announced to a surprised scientific community that the plutonium here had moved, and quite quickly.
At Hanford, Washington, some studies there show that plutonium would migrate 10 centimeters in approximately 240,000 years. Now, it appears from the data we have at Maxey Flats that it's migrated tens to hundreds of meters in 10 to 12 years.
Most early experiments had indicated that plutonium would tend to stay put in the ground. At Maxey Flats, the plutonium moved millions of times faster than expected. It's only one example of new information proving earlier assumptions to be wrong. But for Britain, perhaps the most important new finding from America is the claim that, contrary to our present belief, plutonium and other transuranic actinides don't stay locked in the sediments at the bottom of the sea. Dr. Vaughan Bowen was the official US delegate to the International Atomic Energy Agency conference on dumping radioactive waste at sea. He's one of the world's experts in the field.
To my mind, the most serious ways in which our earlier predictions have been shown to be wrong are twofold. One, that these elements we had originally thought were very immobile in the environment, that once they had associated with soil, with rock, with marine sediments, they would stay put almost indefinitely. And this is turning out increasingly to have been wrong. They do move through soil, they do apparently move through sediment. We have a good deal of trouble now predicting directions and rates of movement.
In 1952, the British government first allowed the release of radioactive low-level liquid waste into the Irish Sea. The British assumption has been that plutonium and the other actinides would sink rapidly to the bottom and stay locked in the sediment, a view now questioned by Dr. Bowen.
It was at one time assumed that this would be acceptable and perhaps even advantageous, because we then believed that these elements, once in the sediments, stayed in the sediments. We have now a great deal of information indicating that this is not true, that they are mobilized in the sediments. In many cases, we don't know what the chemical processes involved may be. There are some data indicating that this may be a change in the reducing state of the sediment. There are some data indicating that it may be as a consequence of the release in the sediment of organic compounds that complex them. But we know that they can leave the sediment again.
Dr. Bowen's research is based on findings from 3 separate locations off the east coast of America. There he studied transuranic actinides from nuclear weapons test fallout and their behavior in the sediments. He's found that, contrary to previous expectations, these substances don't remain locked in the sediment, but remobilize back to the surface of the sediment. This surface sediment itself moves around. What Dr. Bowen fears is that the transuranic elements accumulated over many years will, under certain unusually violent storm conditions, be thrown up onto the beaches. Once on the beaches, they'll dry out and resuspend as dust and blow inland with the winds.
What I'm concerned about primarily is the sudden catastrophic remobilization of a large fraction of the accumulated many years delivery, so that in a given year, instead of the Irish Sea having to accommodate in its biotic environment only the annual output that year from the wind scale operation, it suddenly has to accommodate biotically that wind scale output, plus I could conceive easily of conditions that would permit it to see, in addition to that, 90% of all of the transuranic elements at wind scale had ever released into the Irish Sea. We do know that under infrequent violent storm conditions, really large amounts in terms of total accumulated sediment in estuaries or even quite a ways out on the bottom of shallow seas like the Irish Sea are resuspended, thrown up on the beaches in storm waves or in storm surges, and then are left there when the water recedes, oftentimes to be dried out and finally resuspended as finely divided dust, which is blown for considerable distances. This is especially of concern in the context of the transuranics because of the fact that they are certainly very efficiently absorbed through the epithelium of the lung in virtually all air-breathing mammals.
The ways in which radioactivity gets to man are called pathways. There are many such pathways. Breathing air contaminated by radioactive dust is a direct one, but there are much more complex indirect pathways. For instance, seaweed can take up radioactivity from sediment. Fish can feed off the seaweed. Fish can be made into fish meal and then fed to cattle. And cattle become beef. So Dr. Bowen's concerned about a sudden increase of radioactivity in the Irish Sea.
The effect of that would be a really violent overloading of those pathways for the transuranics that are now identified as critical. And I believe it would result in the introduction of these things in unacceptable amounts, in a considerable number of very much more widespread in a population distribution sense pathways, which are now thought not to be critical at all.
The job of supervising and monitoring the radioactivity is carried out by the Fisheries Radiobiological Laboratory, a section of the Ministry of Agriculture and Fisheries. Their scientists take samples from the water and the beaches, as well as examining fish and other marine organisms to make sure that the levels of radioactivity don't exceed the permitted limits. The problem with this approach, according to Dr. Bowen, is that it only monitors today's dangers today. But the actinides, which remain radioactive for hundreds of thousands of years, are being pumped into the Irish Sea each year in the belief that they'll stay locked in the sediment, an assumption that, as we've heard, Dr. Bowen believes to be false.
I believe that the statement that the present levels of radioactivity in the Irish Sea give us no cause for concern is true only in the short term, that it is correct that it is not now possible and has not ever been possible to demonstrate any present effect from them in terms of damaging either the ecosystem or of hazard to the populations around the Irish Sea. I don't believe that we have enough information to make it even remotely plausible for us to say that this will continue to be true for another 5 years or for another 10 years or for another 25 years. And to be able to extrapolate data even over relatively short times like that, one would have to have a different kind of data from those now being collected.
So you would say that there is cause for concern?
I feel considerable concern.
The fears of Dr. Bowen came at a time when the level of actinides and alpha radiation in the Irish Sea had been steadily increasing. When they first started discharging alpha radiating wastes, the government imposed a limit. In 1957, this limit was 1,800 curies a year, and they released 3%. By 1970, it had risen to 84%. Then the limit was tripled to 6,000 curies a year. By 1974, they'd reached 76% of the new limit. The limits are set by the Ministry of Agriculture and Fisheries. Dr. Bowen's view about the possible behaviour of the sediments in the Irish Sea challenges present British safety standards. But while questioning other scientists in the United States, we discovered the possible consequences of disposing of our low-level nuclear waste are also causing concern in another quarter. The findings of these American scientists are starting to challenge the present assumptions about how much exposure to radiation the human body can take. The need for re-evaluation is being called for by men of great authority. Dr. Carl Morgan was involved in the earliest research on the health effects of radiation and helped to set the original standards for actinides.
I think our present standards for plutonium and the other actinide elements are remarkably good in view of the way they were set. From the beginning of the committees that set the doses for the actinides and all the other radionuclides, the committees of both the International Commission on Radiological Protection and our National Council, I was chairman of these committees for this period of well over a decade. And the levels that we set for plutonium and the other actinides were actually based on only 3 mice. These were studies that were carried out at Berkeley, and it was all the information we had during that early period. In retrospect, I think we were very lucky that the levels we set were as close to an acceptable value as possible. Now, however, that we have some additional information, now that we have studied many effects on many animals, on few studies on primates, but most of them on mice and rats and dogs. I believe that the present standards should be made a bit more conservative by a factor of perhaps 200. That is, the present permissible levels, I think, should be lowered by a factor of the order of 100 or 200.
The reasons scientists like Dr. Carl Morgan want the radiation limit for actinides reduced to 1/200th of the present level are some new research findings which have challenged the past thinking on the effects of low-level radiation. Until recently, scientists believed that a dose of radiation given all at one time would be much more harmful than the same dose spread over a period. And they also believed that the effects of radiation on the population would decline in direct proportion to the dose. It was on this basis that they set the existing standards. But now new findings indicate that dividing the dose into a number of small doses may be more dangerous than originally supposed. At the US government Argonne National Laboratory, Dr. John Ainsworth heads a program studying the effects of various levels of neutron radiation on mice. Dr. Ainsworth's findings suggest that the effects of very low levels of radiation on the general population may be worse than was originally anticipated.
The effects on life shortening are the ones that we have analyzed so far. And the limited dose response data that we have suggests that the effectiveness per rad is greater at a low dose than at a higher dose.
Mice exposed to one high dose of radiation of 240 rads in Dr. Ainsworth's experiments were found to die on average 240 days earlier than non-radiated mice, while mice exposed to the same total amount divided into 24 separate doses were found to die 336 days earlier, a difference of nearly 100 days.
In males, we find that giving a total dose of 240 rad in 24 10 rad doses a week apart produces some more life shortening and an earlier appearance of some tumor types than results from giving the total dose in one episode.
Experiments on mice and other animals have had to provide the basis on which the standards have been set. There's very little information on the way humans are affected by radiation, but large numbers of people in Japan were exposed to low-level radiation after the atomic bombs were dropped on Hiroshima and Nagasaki at the end of the Second World War. These unfortunate victims provide the largest sample of human beings exposed to low-level radiation.
Now, in the case of the Japanese data, the surprising thing was that as one went increased dose, it seemed that the efficiency of induction of cancer was somewhat less rather than greater at higher doses. Or looking at it the other way, that at low doses, we got a little larger effect than one would have expected.
Dr. Baum believes this happens because some members of the population are particularly sensitive to radiation.
If this is the case, then you would expect these individuals to respond at low doses, and there could be a saturation where all of these individuals had been affected, so that at higher doses, only the less sensitive part of the population would be responding.
The theory that Dr. Baum feels explains his findings is that a small part of the population may be more susceptible to cancer because of their genetic makeup. In a simplified cell with, say, 5 components, for a cancer to start, each would have to be damaged. Although they appear quite healthy, some people have some damaged components at birth, and as a result, far less radiation is needed to induce cancer in them. No one can tell if they're part of this group for whom low-level radiation is a much greater risk. This finding is supported by Dr. Erwin Bross from evidence gathered in his study of children with leukemia.
As human beings, none of us are perfect, at least genetically. We all have some degree of genetic damage. Some have a lot more than others. And the persons who are out at the far end of this distribution are close to the brink. If they now get exposed, a certain number will be pushed over the brink into the group that will be very vulnerable to not only leukemia, but a great many other diseases.
On the basis of his research findings in 3 American states, Dr. Bross believes that inside the group born with genetic damage, the risk of developing leukemia is increased 50 times. For them, the unseen danger of radiation is a constant threat, and the radiation standards haven't been set with them in mind.
It's not an easy hazard to detect. You don't just drop dead when you get irradiated this way. The proportion of persons affected by radiation may be a small fraction of the total number exposed, perhaps 1%. And then the actual effects may not show up for many years. In the case of leukemia, probably 5 to 10 years. In the case of other cancers, it can be even longer, 15 to 30 years. And finally, there is this very subtle hazard, which is of special concern to us, where the effect doesn't show up to the children and the children's children. In other words, you don't see it in the person exposed, you see it in the children of the person exposed.
The fear of these scientists is that nuclear power may confer its benefits on society at a price which has to be paid in human health. But there's a major difficulty in assessing that price. It isn't possible to take an individual case of cancer and establish what caused it, and the same is true of most genetic defects. The uncertainty about the penalty which may have to be paid by this generation or those unborn is the great question mark against nuclear power as the energy source of the future. Certainly there are those in the American scientific community who do seriously question the present British practice of pumping waste into the Irish Sea. The radiation levels were established at a time when scientists had less cause to be worried by the possible consequences.